Next, we're going to hear from John Ackermann, N8UR, talking about the clock module design for the Tangerine SDR. Take it away, John.
Okay, thanks, Nathaniel. Let's see if I can get the sharing to work here. Okay. Alrighty, well, Scotty's given a good introduction to the overall Tangerine SDR concept, and I'm going to talk about the clock module, a little bit about the design and architecture, but I'm going to spend most of this time talking about one of the design challenges we have, which is understanding what the real requirements are in terms of performance for the clock system, because that has some very tremendous impacts. And then I'll also, along the way, talk a little bit about some comparisons of different GPS modules that I have been doing as part of our goal to find out which is the optimum cost performance ratio. So as an overview of the clock module, it's a GPS disciplined oscillator that has a set of minimal outputs plus a couple of optional ones depending on the requirements. Its main purpose in life is to provide the 122.88 megahertz required by the receiver module ADC, analog to digital converter, and the transmitter module DAC, digital to analog converter. It also needs to provide 1 pulse per second for time stamping, because one of the important features, particularly for interferometry, as well as other purposes, is that we can align samples across radios. And a time of day message, so we can take that pulse per second and convert it to what time it actually is. Optionally, we can provide a 10 megahertz output for external use, and also optionally we can provide a number of synthesized outputs that could be anywhere from 100 hertz to over 1,000 megahertz in frequency. One of the key features of the module is that it is designed to be extremely modular, and all of the components talk primarily to a single FPGA that's on the module that acts as a switch matrix as well as doing other processing tasks. And we can populate the circuit board with the components that are appropriate for the required performance or functionality. Also, it's going to be usable separately from the Tangerine SDR. As Scotty mentioned, the more use cases we have, the higher volume we can build, which means the lower cost. So by using a daughter board, we can plug the clock module into, for example, a Raspberry Pi and do the Raspberry Pi, or allow the Raspberry Pi to do the control loop processing and whatever other activities the user might want. So we really are thinking of the clock module as ultimately being sort of a time nuts toolkit that can be used to build all sorts of capabilities at different cost points and provide different performances simply by using appropriate components on a single board, which again gives us more volume and lower cost. Here's the overall hardware block diagram, and as you can see in the middle there is the FPGA that every component talks to. There will be a GPS module, and that will provide both a serial data stream as well as a pulse per second signal. There'll be a phase detector, and that's an important part of a GPS disciplined oscillator because it's going to tell you how different the local signal timing is from the GPS, and you use that as part of the control loop. It will have the capability of providing using a 10 megahertz oscillator that can be controlled via a digital analog converter to get the more traditional 10 megahertz GPSDO capability. But again, for the Tangerine SDR, the key thing is the 122.88 megahertz, and that is this module on the left, which has a crystal oscillator running at that frequency and a distribution. We need 4 separate outputs. So there's a buffer driver that provides 4 sets of differential outputs. And again, that oscillator is steered by a DAC so that it can be controlled either in terms of the 10 megahertz or potentially directly by the GPS. There's another alternative in the design that instead of using a crystal to get the 122.88, we can use a synthesizer chip that's driven by 10 megahertz. And there's some trade-offs in that that I won't go into now, but that will provide us the option of generating either the 122.88 or other frequencies as well. And then the FPGA will output communications, pulse per second, and 10 megahertz to the rest of the data engine for use as needed. So the key thing and the question that I have for you today is exactly what requirements the science community has. So we'd like you to tell us both what you want and what you need, because there is a price delta between the two. And if you're as old as I am, you are now immediately thinking of the Rolling Stones, and you can't always get what you want, but if you try sometimes, you just might find you get what you need. So we're hoping that the conversations that will happen perhaps during and after this meeting will lead us to an understanding of what those requirements are. And there are really 5 of them in the clock module, and I'll talk about these in more detail in the next slides. But first is the absolute frequency accuracy and the long-term stability. In other words, how close is the frequency to the cesium clocks in Boulder, Colorado? And how much do we know that we are on the same frequency as everybody else? The second is short-term stability, which is how much the signal wanders around. The third is phase noise, which is how much phase modulation is on the ADC, DAC clock source, because that modulation is in effect pollution, and it will cause a muddiness of the timing edges from the samples that we receive and reduce our ability to precisely measure them. Then there are 2 other aspects, which are the accuracy of the timestamp. In other words, how closely does the time on the Tangerine track U.S. Naval make my mouth work, U.S. Naval Observatory, which is the U.S. time standard. And then finally, just as with frequency, there's accuracy, but there's also stability. How much jitter is there on the timestamp signal? And so those 5 characteristics are the ones that we need to understand in order to do the final design of the clock module. So talking about them in sequence, the first is the frequency accuracy and the long-term stability. And when we have a GPS controlling the system, that's typically the limiting factor. But if we're freestanding, the crystal oscillator aging is dominant. If we're running a GPS system, it's realistic to have parts in 10 to the 13 of absolute accuracy and stability when measured over 24 hours. And parts in the 10 to the 13 is effectively about let's see, that's I think 100 microhertz at a gigahertz. And I may be off a little bit on my scientific notation there, but you get the idea that that's pretty darn good. But in addition, there's a question about the short-term frequency stability and how much does the signal wander around over seconds or minutes or hours. And that is controlled more by the oscillator that's on the local system and is very much dependent on the quality of the oscillators and therefore dependent on how much money you're spending. I'm sorry, that was a okay, there we go. Sorry, for some reason it went backwards. So here is what a GPSDO does in one slide. Those of you who might be studying this, you now have a semester that you can take off. Because all that's happening in a GPS disciplined oscillator is that we are taking the performance of a local oscillator, typically a crystal of some sort, and using that in the short term for stability, but in the long term using the GPS signal. In other words, we're locking the local crystal oscillator to the GPS. And on this chart, and I'm going to spend a second talking about how this chart should be read because it's used extensively in the time world. This is a chart of Allen deviation, which is sort of like like standard deviation, but for reasons that I barely comprehend and certainly cannot explain, standard deviation doesn't work well with the type of noise sources that we find, or the noise processes that we find in clocks. So Allen deviation is used instead, but it's very similar conceptually. The y-axis of this chart is the amount of wander or noise that we would expect to find in fractional frequency terms. So in other words, 1 in 10 to the 7th is 1 hertz at 10 megahertz. Or it would be 1 microsecond at 1 second. So it's a fractional representation of the carrier frequency. And lower is better. These are orders of magnitude apart. On the right-hand side, or the x-axis is the time. So what we're looking at on this chart is that if I take a sample every 10 seconds of the GPS signal, I would find noise of about 1 in 10 to the 9th, or about 1 nanosecond at a 1 hertz pulse per second signal. If I average at every 100 seconds, if I take a sample, I'm an order of magnitude better, because that's the way the noise in the GPS system works. That's essentially a straight line with a -1 slope down until we get into the low parts in 10 to the 13th or even lower. So what we're looking at here is how much noise I would expect to find on my signal. This is the GPS. This is a very low-cost, temperature-controlled or temperature-compensated oscillator. This is a somewhat better oven-controlled oscillator, and you can see that the GPS is quite noisy at short measurement intervals, and it keeps getting worse if we look further to the left, whereas the TCXO is pretty good and the OCXO is much better. Well, what I want to do in a GPSDO is have a control loop. It's typically a phase lock loop that has timing constants, so that I get this performance in the short term and this performance in the long term. And you can see from this that depending on the quality of the crystal oscillator, I have different time periods before that intercept point happens. So by choosing the crystal oscillator, and to a much more limited extent by choosing the GPS, I can design for different levels of minimum performance across any measurement time. That is the key challenge and what we need to understand. Here are several oscillators with typical short-term stability. And again, we're looking here 10 to the -8th at the top, 10 to the -14th at the very bottom. And going from, this is actually a current HPSDR, the Hermes system, the Tapper and the Open HPSDR group designed several years ago with no special oscillator design at all. This is that TCXO again. This is an inexpensive oven-controlled oscillator. This is a rubidium oscillator, which is a different type. It's an atomic oscillator that is sometimes used. And this is an extremely good crystal oscillator. In fact, this crystal oscillator is so good that the only thing I can compare it against is a hydrogen maser. So you'll see there's a huge performance difference here. These are orders of magnitude. And unfortunately, the price is almost at that rate. This is about a $5 or so component. If you want this, it's about $15,000, and you have to wait 6 months to get one. So depending on your budget, we have very different criteria.
5 minutes, John.
Okay, thank you. This is the receiver performance of a number of u-blox GPS modules. And there's basically about half an order of magnitude difference with a price difference. The cheapest one is about $25 in quantity. The best one is about $150 to $175. So there is some difference in performance here. It's not huge, but we have a decision to make in that regard as well. In additional performance criteria, which frankly are easier to deal with, are the phase noise, which again is the modulation that's imparted onto essentially the local oscillator. And In the Tangerine, that's really dominated by the 122.88 source. And there are realistic targets that we can achieve for about the same amount of money. We can't go much cheaper and have a system that works. That's about minus 100 to minus 115 decibels reference to the carrier at an offset of 100 hertz, and about a noise floor in the minus 145 to minus 160 range. There's not a huge difference in price between the better and worse points, but there are differences in capabilities, and we'll need to make some decisions about what is the minimum phase noise that's required. But that's a much simpler issue than the frequency stability issue. And finally, there's a there's timestamp performance. And again, we have accuracy, which is when our clock ticks, how accurate is it compared to the US Naval Observatory. And with these low-cost GPS modules, it's extremely easy to get 100 nanoseconds of accuracy. To get 10 nanoseconds is difficult with consumer-grade equipment, but with good user care, which involves measuring cable lengths and delays, and possibly some temperature control, 10 nanoseconds of absolute accuracy is achievable. Better than that is frankly not practical. In order to achieve those levels, you need to use satellite time transfer or fiber optics and temperature controlled antennas and lots of other things. So really, I think we can assume that the 10 to 100 nanosecond range will be able to achieve in the Tangerine, with most of that difference being dependent on the care with which the system is set up. Now, the raw the timestamp, how much noise there is on that pulse per second signal, depending on the receiver you use, there's about 4 to 20 nanoseconds of peak-to-peak noise that we'll see on that signal. So that may or may not be sufficient for the timestamp that gets put on the data. And there could be occasional excursions that are 10 times that much. But if we use a pulse per second signal that's smoothed from the GPS disciplined oscillator, that we can get well below 4 nanoseconds, which is getting into the amount of time that it takes a logic gate to switch. So we should be able to achieve pulse per second stability in the handful of nanoseconds range for use in the time stamping. To the extent that I have time left, these are a few more pictures of the relative performance of the GPSs that I thought you might find interesting. First, this is a zoom in of the jitter on several of the receivers, and it's probably a little bit hard to read, but these are different generations of the U-Blocks receivers, and you can see that there is a range from this green probably being the noisiest, which is also the cheapest receiver, to this red, actually this red is one of the an interesting units that's more expensive than some of the others, but it has a much lower jitter level, and you can see in ranges in between. You'll also see that some of these are very much a straight line. The GPS itself has some temperature compensation to keep it more accurate, where others, like this purple line, you can sense there's a frequency cycling trend, a bit of a sine wave going on here. I don't know quite what it's from, but that's because of the lower quality oscillator in the GPS unit. Now, there's an interesting aspect to the modern GPSs. They will tell you in advance what some of the noise characteristics of the next pulse per second signal will be. And if you use that correction information, you can get better short-term performance. And this is an example of the same receiver module. The red line that's got the straight slope is the GPS running by itself. This one is from a CNS Systems clock that uses a hardware system to correct for that noise that the GPS is telling it is coming. And you can see that out even to 100 seconds, that is providing better performance. And we can use that correction in our design as well. So the plot that I showed you earlier is actually a little bit less than we'll be able to obtain. We can get some amount of improvement like this simply by using the and again, here's a difference in the yep in the GPS timing between that smooth version and the raw, and that's it. So I will unshare, Nathaniel, and hand it back. Thank you.
Great. Thank you very much, John. I really appreciate it. As a reminder to all participants, there is a link to a Google Drive doc that you can go and you can ask questions in, and we'll ask the presenters to also go in there and answer the questions. Please write your name down when you are either answering or asking questions so we know who asked. All right.
Okay, Nathaniel, well, just one last thing. Yes. I will be posting a much updated version of this presentation to the shared site to replace the one that's currently there.
Wonderful. Thank you very much, John. I really appreciate it. The presenters to also go in there and answer the questions. Please write your name down when you are either answering or asking questions so we know who asked. All right.
Okay, Nathaniel, well, just one last thing. Yes. I will be posting a much updated version of this presentation to the shared site to replace the one that's currently there.
Wonderful. Thank you very much, John. I really appreciate it.